Hello, hello. Hello everyone. My name is Hai. I'm from Rise. We are a chain L2 focused on chain performance. So pushing gigagas per second and transaction per second and forward is our jobs. And so I'm going to spam that a lot today. Would definitely surpass 12 mentions of gigagas. And today I would like to talk about parallel EVM and its contributions to the Quest. So essentially, parallel EVM is a execution engine for EVM blocks that maximize throughput by executing transactions in parallel. It is not the most powerful component in our stack, but it's still a key component regardless to unlock 1 gigagas per second and 100,000 transactions per second. And so traditionally, EVM executors just execute transactions one by one, sequentially, regardless of how many CPUs a node has. And this is obviously like a waste of resources. And ideally, we would get something like 10x speed up by executing 16 transactions at once instead. But it turns out it's not that easy. If so, everyone has done it already. And so the main problem to the is the called state conflicts. And let's see an example to see how it works in practice. So let's say, so let's start with Alice having 10 ETH. Then in the first transaction, he sent 2 ETH to Bob, and now he has 8 left. And in another transaction, in the next transaction, he sent 1 ETH to Carol, and now he has 7 left. So this is very simple and intuitive in the sequential world, right? But when we go parallel, it's got a bit tricky. So if we execute these 2 transactions in parallel, it will read that Alice have 10 ETH both. And the second transaction would actually think that he would have like 9 ETH afterwards, which is obviously wrong. And the issue would arise every time 2 transactions try to read and write to the same state. And to solve this, we have like block STM, which is a algorithm designed by Aptos, especially for MoveVM and their own chain back then. And they solved this problem by adding a multi-version data structure that track read and read data per transaction, and by introducing validation tasks. So a scheduler would schedule both execution and validation tasks to see if transactions were executed with old data, and if so, it must be re-executed with the latest data stored in the multi-version memory. So if we get back to this example, then a validation task on the second transaction would notice that, okay, it was executed with an old balance of Alice, so it would reschedule the transactions to be re-executed with 8 ETH instead. And it turns out it's not, block STM is not that applicable to EVM off the bat, because like all EVM transaction read and write to the same beneficiary balance for gas payment. So for example, like in this transaction, sorry. Okay, sorry. So we start with a beneficiary balance of 10 ETH, and the first transactions just pay 0.2 as gas. Then it has to calculate this as, okay, so after these transactions, the beneficiary balance has 10.2, and to the next transaction, it has to read like, okay, so after the previous transactions, it has 10.2, and now we pay 0.3, now it's 10.5, and this repeats to the end of the block, making the block like fully sequential by definition. And so there's essentially no parallelism for EVM. If we just stick to block STM at least. And so luckily, I had some weird experience writing production Haskell for a few years. And so intuitively, I came up with a very purely functional way of doing things of lazy evaluations. So the solution is like, instead of eagerly calculating the beneficiary balance at the end of each transaction, we simply lazily update, like restore these updates like, okay, I don't care what this current value is. I just want to, oh, sorry, I keep misclicking. So I don't care what the current balance is. I will just add 0.2 to it as gap payment. And for second transaction, it doesn't have to read the current balance at all. Just say whatever it is. I'm just going to add 0.3 to it. And so we only fully evaluate this at the end of the block or when there's an explicit read to the beneficiary balance. So the full evaluation is still sequential, but it's very simple addition, and so it's very fast. It's still very fast. Why with these lazy evaluation techniques, we can do state loads, EVM execution, opcode interpretations, gas calculation. All of that can still be doing in parallel. And at the end of the day, if we look at the whole point of block execution, that we only want to know like the state at the end of the block, and all these intermediary state we don't really care about. And so, and it turns out that gas payment is not the only thing that we can lazy update. And we can do the same for pure e-transfers or ERC20 transfers and more. Because if we look at it, then for the sender of a raw transfer transactions, a lazy update would be like, I don't care what the nonce the current nonce is, we're going to add 1 to that. And I don't care what the current balance is, I don't need to eagerly calculate that just yet. And I'm just going to add a minus subtract by the transaction value plus the gas payment at the end of the block. And so by that, even if the same sender have several transactions in the same block with increasing nonce, it can still be parallelized. And same for ERC20 transfers, which is basically just adding something to the recipient balance and subtracting something from the sender recipient. And it also turns out that EVM transactions have a long queue distributions. Basically means that like a few transaction patterns make up for most transactions. So if we can detect the patterns and optimize to it with lazy evaluation, lazy updates, or any other techniques, we can gain huge speed up. And so we also do a lot of benchmarking for any performance works. It's a must. And through these benchmarks, we can also like detect what are the bottlenecks, what can be improved, especially when we are building on block SDM, which was originally designed for EVM, which is very different from EVM. So through this benchmark, we can actually see a lot of improvements specifically can be done for EVM. And so the current status is that we are 2 times faster on average. This is like 2x speed up over sequential execution for Ethereum mainnet blocks, and the max speed up is our 4x. And interestingly, we actually have little to no overhead as we fall back to sequential for small blocks, and lazy updates actually remove most of the conflicts. So this is an improvement over block SDM, which has like 30% slowdown when a block is very sequential. But if we look at this, then it is not that exciting, right? Like, I mean, like if it's not 10x or 100x, then what's the point of even talking about this? So we have to move to the next benchmark, which is the gigagas benchmark, because our goal at the end of the day is to push EVM throughput forward, and to surpass 1 gigagas per second, 100,000 transactions per second, and a lot more. And this is like a lot bigger than what is the current traffic on Ethereum today, and we are benching with very large blocks with 100,000 of transactions, and to see how parallel EVM can speed this up. And it turns out the max speed up we achieved so far is actually 23x, and this is for over 6,000 independent Uniswap transactions that make up to 1 gigagas. And another interesting number is that this is done in only 18 milliseconds. So this scales up to 55 gigagas per second, which is not bad, I guess. But when we plug this into our own, this 55 gas per second is just raw execution speed, right? When we actually plug it in the whole block building and syncing pipeline, it only scaled to not even half of that, to only 21 gigagas per second. And this is because like raw execution is still only 1/2 of the bottleneck, and the other half, the actual bigger half, is on state access. And we need to solve that through a lot of the other techniques that hopefully we can share more about in Frontier 2025. But for now, let's just bear with me that with parallel EVM, we can get to 21. Actually, if we only apply parallel EVM to vanilla Reth, then it's only get to around 7 gigagas per second peak throughput for live block building and syncing. And this 21 is with other improvements that we've done already on the pipelining improvement and also like the state access improvements. And of course, like, okay, so 21 gas per second is like 3,000 times faster than the peak speed of Arbitrum. But if we look at the slide, then there's a big red flag. It's called independent. So is this even realistic? Like, I mean, like all these measurements are on independent transactions. While in practice, like many Uniswap transactions are dependent on the most popular pools, right? So this is like fantasy, if anything, it's useless. But it turns out that there are already many efforts in the ecosystem to design parallel DFs. Just like when we started to have like multi-core machines, people started to design, you know, concurrent and multi-processor algorithms. And I think we are entering the same area, and Ethereum is actually lagging behind a little bit. And you can see in these kind of papers, then other ecosystems already are designing parallel DApps, like shorter automated market makers that is promised like 5x throughput on Sui and 16x throughput on Solana. And so I hope that, you know, our PVM could help, you know, bring all these innovative design and more to Ethereum and all the L2s to keep EVM contract design cutting edge. But also, like, not all usage are dependent. So there are actually many usage that are independent by nature. So we've been in talk with a project called EVM that is another L2 that use RV as the cheap storage backend. And they also, you know, support, you know, DA commit transactions for other L2s. And all of these DA commits are independent by default. And so, you know, if they plug parallel EVM into their node, it would be like an instant X3 for nothing. And so we have been working to put parallel EVM into Reth, and it's been a few weeks of work already. And it's not necessarily easy because we need to make sure that parallel EVM works correctly and actually consistently perform well, and not seeing, you know, some edge cases that is much lower than sequential, or it actually produce wrong results. Then we actually have to fix all of them before confidently running it inside Reth. And my favorite edge case is a block where an MVM bot interacts with contract, then self-destructed, redeploys to the same address, interact with the contract again, all in the same block. And our parallel executor needs to know if a address is a contract or not to apply lazy updates rules, and that block surely confuse the hell out of it. And so, yeah, we still need to work on a lot of testing and benchmarks before we can say that, you know, parallel EVM is ready inside Reth. But the overall aim is to at least double or triple the sync speed. And so one day we can sync Ethereum from scratch in half or just under a day. And if we look at this graph, then basically it's, you know, and also like our current work in progress integration is just slightly above 300 lines of changes, because parallel EVM is essentially just a very simple and clear interface. You give me a block, I give you back the state transitions and the execute result of that block. And so it's, if we look at this, then yeah, it's if any projects are using REVM in their stack, can just switch REVM over to parallel EVM to, you know, get instant speed up with the same interface. And also, like, anyone using Reth would in the future benefit from this speed up by instantly. And for future plans, so we only started to work on parallel EVM, I think, in early April, 4 months. And throughout, we already seen like 4x, 7x, 10x, 13x, 17x, and now it's 23x for the peak gigagas speed up. And I don't think it's stopping anytime soon. And we have several ideas to keep pushing the limit. So one of it is already mentioned by several teams, is to support an optional DAG, which is a dependency graph for full nodes to sync from sequential faster. So basically, like the DAG would say that, okay, these transactions depend on these transactions. And so a syncing node with that DAG would just execute all of them in the right order so that there would be no conflicts and no re-execution at all. And so this is also like very important work in the sense that it helps to keep the full node smaller than the sequencer. So the sequencers can be buffed up to very performant, powerful and expensive hardware, but the syncing node can stay, relatively consumer friendly. And also, one of my personal favorite is to redesign the scheduler to minimize synchronization overhead. So I'm actually not a big fan of block SDM scheduler design because it's, all the worker threads kind of share the same atomics. So they kind of like interact with these same atomics every worker iterations, and that keep refreshing the CPU cache. So there's always some kind, it's very small, but there's constant latency per worker iterations, which is very annoying. I think ideally we would have like a dedicated scheduler thread that manage all these atomics internally and going to put the task for each worker thread in their own dedicated memory locations so that all these worker threads only going to work with their own allocated memory locations instead of having to share. And only in the case of state conflicts do they need to, access to the scheduler memory locations to say that, okay, there's some state conflicts pre-revert to the previous transaction index. Other works included optimizing the concurrent data structures. This include the in-memory cache for chain state loaded from disk, and also the multi-version data structure for the parallel executor. We can also track which checkpoints to re-execute from instead of re-executing the whole transaction when there's state conflicts. And one thing I really want to try for months now is to try and support more different EVMs executors, like the just-in-time compiler that Danny, I believe, and the Paradigms teams shipped a while back. So we'd love to try to plug it in and see how it could speed up parallel EVM even more, get even more gigagas. And the last one is to do a lot of low-level tuning. So like memory allocators, like when you optimize to the microsecond or range, even memory allocators can make a big difference. And up to now, we have been trying like jmalloc, snmalloc, memalloc, and rpmalloc. And the difference is actually very noticeable, like up to like 30 to 40% in performance. And these add up. And so we are using rpmalloc mainly for our parallel EVM implementation. But also we believe that in the future, when the allocators API Rust mature and get stable, we'll benefit even more by hand-rolling our own custom allocators for the concurrent data structures and to have like another good one for the as a global allocators for the whole node or the program that consumes and uses parallel EVM. Kernel configurations have a very interesting backstory. So I got 2 weeks ago, I got back from AdCon after a week on the road, and I boot up my desktop, excited to get back to work. And it said it prompted me to update Ubuntu to 24.0, and I was like, a fresh start, why not? And then I updated Ubuntu, I updated the Rust compiler for a fresh benchmark, and out of nowhere there was a 20% regression. Like, I didn't change any code. The machine even had like a 1 week rest. Before that, 16-hour day just benchmarking hardcore code. And why the 20% regression? And after looking around, I found out that is insane. So I think the latest Ubuntu versions, it upgrades the Linux kernel version and actually switched to a new Linux kernel scheduler as the default kernel scheduler. And for some reason, this one is 10% better on average, but 20% worse for computing intensive use cases like parallel EVM. And so we have to roll back to the previous kernel version. And I have to just alert everyone in the team to make sure that you have the right kernel version inside your machine and make sure that all the cloud instances have the right kernel version. And of course, we cannot just get stuck with this kernel version, right? And so I think in the future, we will need to fine-tune parallel EVM to work well with all most common kernel configurations, and especially to have the best one for our own stack. And another one is to an ARM and x86 or AMD6T. This one is pretty interesting as well. So my desktop is a Intel i9 overclock at 5.9 gigahertz, and it beats all cloud instance I could ever find easily. But for some reason, I spun up a AWS instance with Graviton 3 recently, and it's like only at 2.6 gigahertz, and it's literally virtual CPUs versus my physical CPUs, right? And for some reason, the cloud instance beat my desktop at the unit 12 gigahertz benchmark, and that 18 milliseconds is actually from that Graviton. And so I think that eventually we also need to do all of these low-level tuning to make sure we know exactly what is the best configurations and what is the best setup to deploy parallel EVM on, and at a higher level, like to deploy all these performance nodes on. And so, so we are fully open source, and the parallel EVM implementation is fully in Rust, in MIT licensed, and so, let's collaborate. If you have any new ideas, feature requests, collaboration ideas, integration ideas, or new parallel DApp designs, feel free to hit us up. And we're actually also hiring. So if you're interested in doing hardcore, low-level Rust performance tuning works, for this and for a new database that we have been cooking on the back, then feel free to hit me up. And again, a great thanks to Paradigms and the team for hosting this nice event and building Alloy, REVM, Reth, and a lot more that could make parallel EVM happen so quickly. Thank you.
Andrew, hi. We have a question from Christian.
Thank you for the presentation. I have two quick questions. One is it possible to run this optimization for a whole range of blocks so that, I don't know, you kind of have, maybe you can make the syncing faster? And what kind of gains do you think you'd see for like full ranges as opposed to parallelizing each block independently? And the second question is, I saw that you restart transaction execution from scratch upon conflicts. I was wondering if you can hold the intermediary state in some kind of immutable data structure so that you can resume basically from any program like instruction.
Yes, thank you for the good question. So for the first one, it's definitely a possibility. So I do expect that. So BlockSTM essentially takes in an input as a list of transactions, so it doesn't really need block headers. So block headers are only relevant in setting things like what is the beneficiary account and such. And so we can definitely flatten a lot of blocks and try to run it through parallel EVM for potentially more parallelism. And especially if we look at this, then the intuition so far is that the more transactions and the more workload we have, the more parallelism we can potentially has. Because also, like, I think until now, one of the biggest bottleneck that I want to get rid of is when we join threads. It actually has a pretty long latency, especially in zip Rust. And so I think that if we can do a lot of stuff before we join the threads and output a execution result, the better. And also that's also a reason why that ARM thing that could beat my desktop was because I think ARM is very efficient, and so it has very low thread overheads, and so we can spin up new worker threads and join them much faster. And so definitely that's something we want to try in the future. So especially for historical sync, just buff a lot of blocks together and execute them in parallel. And for the second question, it's definitely the first bullet point here. So this is actually, I stole this from the original BlockSTM paper. I don't think they have tried to implement that yet, but I think it makes a lot of sense because re-executing from scratch is very expensive. We need to set up the EVM environment and all these configurations for each transaction. That is very expensive. And so we just re-execute from the read point that flag a state conflict, then I assume that will be much faster.
question here. So for these future plans, which one of you do you think will be the biggest like super boost for real world transactions? I mean, we saw that like with independent Uniswap transactions, the performance already like amazing, good enough. But for real world transactions, like which one of these, like is it a better scheduler other than Block SNT, STM, or some other optimizations that's gonna take us there?
Yeah, that's actually a very good question. So I actually think that the most probably promising gain out of this is the first one, is to just support like optional metadata for the syncing nodes or whatever follows to run and execute the transactions in a way that there will be no re-executions, no state conflicts. That it would actually speed things up. I think all of the others are more on it's very hard to speculate like how much it would affect real transactions. It could be anything from just 20% or to 200%. So it's a lot of experimental work required to understand that. But also I believe that the new parallel designs for the apps would be also required to get the best out of parallel EVM, because we can only do so much to remove explicit read, because lazy updates is a very powerful technique, but it cannot be generalized to arbitrary logic. And so I don't think we can just use the ad hoc techniques at the parallel EVM level to solve all the apps, and they will actually have to design better, stateless apps instead.
Hey, great talk, really interesting work. You didn't speak much about so the EVM wasn't ever designed to really be parallelized, right? I work on L2s. I'm sure a lot of other people who work on an L2 would be open to adopting L2-specific EVM extensions. So if you could pick one or two things that you would change in the EVM to enable more parallelism through the sorts of techniques you're using, what might they be?
I know this is hard to take, but I would switch to another VM. Incrementally. Well, it's pretty hard to say, because I still believe that more state conflicts at the app level, so it depends on the application's logic. So as we can see with the previous example of Weave VM, they use case are all all transactions in the DA commitment use case are independent by nature. And so, we don't need to change EVM to get the max parallelism level out of it. But yeah, I guess like a low-hanging fruit would be, to remove, to modify the gas payment mechanic, because as you can see, this lazy technique can, get that through, but there's still a cost at the end of the block, to fully evaluate these sequentially. And it does add some, tail latency to the block execution result, which is very undesirable. So I would change that to first.
Another idea is to introduce an increment opcode, which allows you to get around the S-load add S-store pattern that happens in
so basically providing more opcodes for the apps to design better or easier design parallel the apps, that would be very helpful.
Okay. One question there, one from Zero Edge, and we wrap.
Yeah, two quick things. The system you described reminds me a lot of like a lazy MapReduce. Have you looked into doing more DAG-based approaches to scheduling work based on like what slots are accessed?
Yes, certainly. So we are one of another component in our stack is a customized mempool that do some pre-processing of the transactions to do statistical analysis to detect dependencies to but this only applies for block builders. But at least like for block builders with this technique, it definitely helps by reducing the state conflicts file at runtime, which is a lot costlier. And so after that, then the block builders can pass on the blocks with this DAG that it already built to the syncing nodes.
I feel like that's like a really promising avenue. And then the second question I had is, how much of a speed up do you have in blocks where you have transactions that actually end up all affecting the same contract? Like pragmatically, you oftentimes see blocks where it's like all transactions being a swap on a Uniswap pool or like a mint on an NFT. It's 1x, or is there like, does doing it lazily actually improve it from 1x?
Lazy is not very easy to generalize, so it really depends on the actual applications. So ideally, application would redesign in a way that reduce shared states between the transactions. So that would help a lot. Until we have that, then would be happy to have. I'm sorry. Just 1 gigagas per second on average, and having this 21 gigagas at the peak that we aim for. And eventually we push the average towards 21 gigagas second. And this is not like from parallel EVM alone, but from the whole ecosystem, pushing these new parallel design forward, working together to achieve this. And hopefully by the time we have the average case 21 gigagas per second, we would start to see like use cases that actually reach 1 teragas per second as peak speed up. Yeah.
All right, last question for Zero Age, and we can wrap.
Hi. One concern with block production being sped up, I think on the sync case, it's obviously a big win across the board. But in block production, if it's faster to produce blocks, then there's a danger of producers just withholding the block production to gain more MEV. How do you see the MEV issue slotting in with parallel execution and other techniques to accelerate block production, or potentially even exacerbating certain issues?
Yeah, that's also a very good question. I think this is harder to solve for L1 or existing blockchains, but I think at least for us, the more we get, the more throughput we get, the lower block time we can push down. Of course, like you have more power to build different blocks, but now you have less time to build. So we try to reduce the block time to improve the UX, but also like to make sure that the best block is built on time and no holding back there.
All right, you're up high.
Thank you.
Okay, so this is the end of the beginning of the day, or the end of the talks part of the day. What's going to happen from now is that we're going to start flipping the rooms. I'm going to ask everyone in a second to stand up. We're going to start from the left side of the room to the right. We're going to replace all the chairs with tables, both here and outside. And basically, for the people that stay, the expectation is to enter work mode and hack. Big shout out to our events team for making this happen, our design team for giving everyone very nice swag, to Cursive for this nice social experience, to the speakers that worked extremely hard to get this done on a very short notice. And we hope to have a great day for the rest of today. Please feel free to hang out until, I think we have it around until 8 p.m. And then tomorrow we will reconvene at again the same time. Please make sure to bring your cards. Thank you all.